Hello, this is checkpoint 4.32. It says we have dimensions of cardboard to be 20 inches by 30 inches. So we have a square cardboard that's 20 inches by 30 inches. And we're going to cut off a corner of that, or 4 corners from there, of square size X. And then they want us to figure out the domain of consideration for X. Okay. Now the idea behind cutting this up like this is to create a box, an open top box. So your open top box would look something like this, where the height here, the thing that was cut off, was X. And so in terms of the domain of consideration, what should X be? If you kind of look at how far this X can go from here to here. If you cut off anything more than that, or anything up to that, you're gonna come up with something that's not a box anymore. And if also you can cut something really small, close to 0, and if you cut 0x, or x is equal to 0, then that's not a box either. So this is going to go from 0 to up to half of 20, so that would be 10. So this is our domain of consideration. You can say that this is equal to, although when you do say that it's equal to, you know that you're going to get a degenerate case where you're not going to have a 3-dimensional box anymore. All right, so this is what the checkpoint is asking, but I think we should go ahead and continue solving for this particular problem. What size should a square be cut out so that we can maximize the volume? So we're going to maximize the volume. We talked about cutting out this X, and if we cut out an X, let's keep it a nice size X over here, where it's not going to be where we can actually come up with a box. So one side of this, the short side, will be 20, but then you cut off an X on one side and then an X on the other side. You're going to cut off 2 X's. So this should be 20 minus 2X. And similarly, you have a side of 30, and then you cut off a couple of X's out. So this will be 30 minus 2x. So it looks like the volume that you're going to try to maximize, the volume is going to be length times width times height. So V, and this is all a function of X already, which is going to be great. We don't have to mess around with any constraints. This is going to be X times 20 minus 2x times 30 minus 2x. Okay. All right. So now we have a function that we can work with. We can try to maximize this function by taking derivatives and things like that. And then we can work from there. So let's go ahead and take the derivative, v prime of x. Well, actually, before we take the derivative, I think it might be a good idea to multiply it all out, because looking at this right now, taking the derivative will involve a couple of product rules. And so to try to avoid that, let's multiply this out. So this is going to be 60 or 600, and then we're going to multiply it times x. So this is going to be 600x. And then foiling this out, the middle term is going to be 60 plus 40, so that'll be 100x minus. And then there's an extra x that I'm going to multiply this by, so this becomes 100x squared. And then the last terms would be 2 and 2 is 4, x squared positive. But then the x squared is going to be multiplied by another x, so it'll become x cubed. So this is a lot nicer to take the derivative of, instead of having to try to do the product rule. So let's go ahead and take the derivative. We're going to get 600 minus times 2 here, so it'll be 200x, and plus this is going to be 12x squared. All right, now we're going to set this equal to 0. I'm just going to go ahead and set this equal to 0 here. Actually, let's put it here. And I think it might be easy if we can factor out a 4. I think a 4 would work. So factoring, and I'm going to factor out a 4, and I'm going to switch to order 2. So this will become 3x squared. And then 4 out of here is 50x. And 4 out of here is 150 positive. All right. So from here we will take, we'll just take the quadratic formula to help us solve for this. X is going to be equal to 50 plus or minus the square root of 50 squared minus 4 times A, which is 3, times C, which is 150, all over 2 times A, which is equal to 3. All right. So this will take a little bit of time, but I actually did some of the work already, and I'm going to get 2x values out of this, one where there's a positive, one where there's a negative, and the 2x values that I get out of this looks like it's going to be approximately equal to, let's just do the approximations, 3.9. Well, let's do the from the quadratic formula. It'll be, it looks like it'll be 25 minus the square root of 175 divided by 3, and I'll leave some space here, and because let's do the equal sign. Let's do the equal sign here, approximately equal to there, comma, 25 plus the square root of 175 over 3. And this is approximately equal to whatever it is. So this first approximately equal to is 3.9237, 3.923, let's call it 24. And then the other approximation is 12.743, 12.743. Now, based on our domain of what made sense, we know that this 12 is out of the domain, so this can't be the problem. That can't be the answer, so it has to be this one. So we would want to cut out an x value of about 3.924. Cut out that much square to maximize the volume. So volume is maximized when x is equal to 25 minus root 175 over 3, or approximately 3.924. Now, if you want to carry on with this problem and figure out what the actual volume is, you would simply put this value that you got, that's 25 minus square root of 175 divided by 3, into your volume equation, the original volume equation, not the prime, and then you're going to get whatever that volume is. Okay, but again, this checkpoint is asking for this. If we went through the whole problem and finished it, our answer x would be this, to figure out the size of the square that we would cut out. And then to actually find the volume, you would plug it back into there. Okay, I hope that helps. Good luck.